Welcome to today's problem walkthrough. We will be exploring LeetCode problem number 212, Word Search 2. This is a challenging yet rewarding problem that combines backtracking with tree data structures to efficiently find words on a 2D board. Let's dive in and understand the problem, approaches, and solutions step by step. In this problem, we are working with a two-dimensional board of characters and a list of words. The task is to find all the words from the list that can be constructed by navigating through adjacent cells on the board. When we say adjacent, we mean cells that are next to each other horizontally, vertically, or diagonally. However, there's an important restriction: once a cell is used in forming a word, it cannot be reused within that same word. The input consists of the board, which is represented as a list of lists of lowercase English letters of size up to 12 by 12, and the list of words, which can contain up to 30,000 strings, each up to 10 characters long. The goal is to return a list of all words from the input list that can be found on the board. The output is a list of strings representing the words from the input list that are found on the board. The order of the words in the output does not matter, but each word should appear only once, even if it can be formed multiple times on the board. To understand this, let's consider example 1. Here, we are given a 4x4 board with letters and a list of words that includes oath, pea, eat, and rain. The output for this example is oath, eat, as these are the only words that can be constructed by following valid paths on the board. Taking a closer look at example 1, we can see how the words oath and eat are formed. For oath, the path begins at the top left corner of the board with the letter O, then moves diagonally to A, continues diagonally to T, and finally ends at H. Similarly, eat can be constructed by starting at the letter E, moving right to A, and then proceeding diagonally to T. On the other hand, words like pea and rain cannot be formed, as no valid paths exist on the board to spell them out. Now let's discuss example 2. In this case, the board is a simple 2x2 grid, and the word list contains only ABG. The output here is an empty list, as ABG cannot be constructed. The reason is that forming ABG would require reusing the cell containing B, which violates the rule that each cell can only be used once in constructing a word. Moving on to the constraints, the board dimensions are capped at 12 by 12, and the word list can contain up to 30,000 words. Edge cases to consider include scenarios where the board has only one cell, where the word list is empty, or where no valid paths exist for any word. It's also important to ensure efficiency when multiple words share the same prefix, and to handle duplicate words in the input list by including only unique matches in the output. To begin solving word search 2, let's consider the brute force approach. This strategy involves searching for each word in the given list by starting at every single cell of the board and attempting to form the word recursively. At each step, we explore all neighboring cells to see if the word can be constructed. While this method is intuitive and simple to implement, it comes with significant computational overhead. The time complexity is proportional to the product of the number of words, the dimensions of the board, and the branching factor raised to the average word length. This makes the approach highly inefficient for larger boards or word lists. Additionally, it suffers from redundant computations, as the same prefixes may be searched repeatedly. While straightforward, this approach is impractical for scenarios with large input sizes, prompting us to look for a more optimized solution. To address the inefficiencies of the brute force approach, we can utilize a tree, or prefix tree, to optimize the search process. The first step is to build a tree by inserting all the words from the input list. Each node in the tree represents a unique prefix, and we mark nodes that correspond to complete words. Next, we perform a backtracking depth-first search on the board, starting from each cell. At each step, we check if the current prefix exists in the tree. If it doesn't, we terminate the search for that path, effectively pruning invalid branches. If the prefix does exist and forms a valid word, we add the word to our result and continue exploring neighboring cells. To ensure cells aren't revisited within the same search path, we use a visited marker. Furthermore, once a word is found, we can remove it from the tree. This prevents redundant searches for words that have already been identified. By leveraging the tree, we significantly reduce the number of recursive calls, improving the time complexity, while the space complexity remains manageable given the compact structure of the tree. After evaluating both approaches, the optimized method using a tree emerges as the preferred strategy. It strikes a balance between time and space efficiency and offers several key advantages. The first insight is that many words in the list share common prefixes, and the tree allows us to avoid repeatedly searching these prefixes. Additionally, pruning invalid paths early saves a substantial amount of computational effort, making the algorithm far more efficient. By removing words from the tree once they are found, we further optimize the solution by eliminating redundant searches. Compared to the brute force approach, which struggles with redundant computations and inefficiency on larger inputs, the tree-based method handles shared prefixes effectively and reduces unnecessary operations. While it does require additional memory to store the tree, the performance gains outweigh this trade-off. Combining the tree with backtracking gives us a clean, efficient, and elegant solution to the problem, making it the clear choice for Word Search 2. To solve the Word Search 2 problem, we need to determine which words from a given list can be formed by tracing adjacent cells on a 2D board. Here, adjacency means you can move horizontally or vertically to neighboring cells, but each cell may only be used once in a single word. Our approach leverages backtracking to explore all possible paths on the board for each word. The process begins by iterating through each word in the list. For every word, we examine every cell on the board as a potential starting point. From each starting cell, we invoke a recursive function to see if the word can be constructed by following valid paths on the board. This systematic exploration ensures that all possible combinations are considered, even though it may be computationally expensive without optimization. The core of the algorithm is the recursive backtracking function. This function works by taking the current position on the board, the part of the word that still needs to be matched, and a visited set to track which cells have already been used. There are two key base cases. First, if the word is empty, meaning all its characters have been matched, we return true. Second, if the current cell is out of bounds, has already been visited, or its character doesn't match the first character of the remaining word, we return false. Once we validate that the current cell is usable, we mark it as visited and recursively explore its four neighbors up, down, left, and right. If any neighbor yields a successful match, we immediately propagate that success back through the recursive calls. However, if no neighbor works, we backtrack by unmarking the cell as visited, allowing it to be used in other potential paths. If the function ultimately finds the word from any valid starting position, we add it to the result list. Once all words have been processed, the result list is returned, containing all the words that can be formed from the board. Backtracking is a natural fit for this problem because it allows us to systematically explore all possible paths while adhering to the constraints of adjacency and single-use cells. By marking cells as visited and unmarking them as we backtrack, we ensure that no cell is reused in the same path. To make the search more efficient, we can prune the search space by eliminating unnecessary checks early. For example, if the first character of a word doesn't match the character in a given cell, there's no need to explore further from that cell. Similarly, if the length of a word exceeds the total number of cells on the board, we know it's impossible to form the word. Additional optimizations can be achieved by using a tree data structure to store the words. By checking prefixes during the search, we can terminate invalid paths early, avoiding unnecessary recursive calls. We can also skip cells that do not match the prefix of any word in the list, further reducing redundant computations. Several data structures are key to implementing this algorithm effectively. First, the visited set is used to track which cells have already been used in the current path, ensuring that no cell is reused. This can be efficiently implemented as a Boolean array, providing constant time access. Second, a tree can be used as an optional optimization to store the list of words. This allows us to perform prefix matching, which helps terminate invalid paths early and avoids redundant checks for words that cannot possibly be formed. Lastly, we maintain a result list to store all the words successfully matched on the board. This list is returned as the final output of the algorithm, containing only the valid words found during the search. Analyzing the algorithm's complexity helps us understand its performance. For time complexity, in the worst case, we consider each word of length L and explore all m times n board cells. For each cell, we recursively visit up to 4 neighbors, leading to 4 to the power of L, recursive calls for a single word. Multiplying this by the number of words, k, the total time complexity becomes k times m times n times 4 to the power of L. For space complexity, the recursion stack can grow up to the length of the word, which is O, L. Additionally, we use a visited set that requires O, M *n space. Combining these, the total space complexity is O, M *n plus L. While this algorithm is computationally intensive, optimizations like using a tree significantly reduce redundant computations, making it more practical for larger inputs. When implementing the algorithm, it's important to account for edge cases to ensure correctness. If the board or the word list is empty, the result should simply be an empty list. Similarly, any word longer than the total number of cells on the board can be skipped during pre-processing, as it's impossible to form. Duplicate words in the input list should be handled carefully by adding only unique matches to the result list. Finally, words with shared prefixes can be a challenge, as they could lead to redundant searches. Using a tree to handle shared prefixes efficiently ensures that we do not waste time exploring paths that cannot lead to a valid word, improving both the speed and accuracy of the algorithm. Here, we start by defining the findWords function, which takes two inputs, the board and the list of words we need to find. To efficiently search for these words, we use the tree data structure. Inside the build_tree helper function, we initialize an empty dictionary called tree, which will represent our tree. We then iterate through each word in the words list, and for each character in the word, we navigate or create the corresponding node in the tree. When we reach the end of a word, we mark it with a special character, hashtag, to indicate the end of a valid word. This helps us quickly determine when we've found a complete word during our search. Next, we define the DFS function, which is responsible for performing a depth-first search on the board. This function takes the current node in the tree, the row and column indices of the board, and the prefix of the word formed so far. If the hashtag marker is present in the current tree node, it means we've found a valid word, so we add the prefix to our results set. Before proceeding further, we check boundary conditions to ensure that the current position is within the board, hasn't been visited yet, and matches a child node in the tree. If any of these conditions fail, we return immediately. We then mark the current cell as visited by adding its coordinates to the visited set and retrieve the character from the board. To explore the surrounding cells, we'll use the directions defined shortly. For each direction, we recursively call the DFS function, passing the corresponding child node in the tree, the updated row and column indices, and the newly formed prefix by appending the current character. Once all directions have been explored, we backtrack by removing the current cell from the visited set, allowing it to be reused in other paths. After defining the DFS function, we proceed to initialize the tree by calling build_tree, and we create an empty set called result to store the words we find. Additionally, we define an empty set visited to track visited cells and an array directions that contains the 4 possible moves, right, down, left, and up. We then iterate over each cell in the board using nested loops. If the character in the current cell exists as a key in the tree, it means that it could be the starting point of a word, so we call the DFS function from that cell with an empty prefix. Finally, once all cells have been explored, we return the result set converted to a list. This ensures that we return all valid words found on the board without duplicates. Here, we begin by defining the main structure of our solution. The findWords method takes a 2D character array board and a list of words as input. The first step is to construct a tree data structure using the provided words. This tree helps us efficiently check if a given prefix exists in the word list. Once the tree is built, we initialize a hash set to store the results, ensuring that duplicate words are not included. We also prepare a visited array to keep track of which cells on the board have already been explored during the search. To find all valid words, we loop through each cell in the board. If the character at a cell exists as a child in the root of the tree, we start a depth-first search from that cell using the DFS helper method. This method will recursively explore paths on the board to identify valid words. The DFS method is designed to traverse the board recursively and check for valid words based on the tree structure. It begins by handling the base cases, if the current cell is out of bounds, already visited, or if the character at this cell is not present in the tree, the method simply returns. Otherwise, we retrieve the character at the current cell and navigate to the corresponding child node in the tree. We also extend the current prefix by appending this character. If this new prefix forms a complete word in the tree, we add it to the result set. Next, we mark the current cell as visited and proceed to explore its neighbors in all four directions: up, down, left, and right. Each neighbor is visited recursively through the DFS calls. Once all neighbors are processed, we backtrack by marking the current cell as unvisited, allowing it to be revisited in future search paths. The build tree method is responsible for constructing the tree data structure from the given list of words. We start with an empty root node, and for each word, we iterate over its characters to build the tree structure. At each step, we ensure that the current character is added as a child node if it doesn't already exist. We then move to this child node and continue the process until all characters of the word are added. Once the end of a word is reached, we mark the corresponding node as the end of a word by setting its isEndOfWord property to true. Lastly, we define the treeNode class, which represents a single node in the tree. Each node contains a map to store its children and a Boolean flag to indicate whether it marks the end of a word. This treeNode implementation is the backbone of our solution, enabling fast lookups and prefix matching during the word search. Here, we're given a board of letters and a list of words. The problem is to find all the words from the list that can be formed by connecting adjacent letters on the board, or letters can only be used once per word. To solve this efficiently, we first build a tree using the given words. The tree is a tree-like structure that allows us to store words in a way that supports quick prefix matching. For the input words oath, pea, eat, and rain, the resulting tree has nodes for each character in these words, with the hashtag symbol marking the end of a word. For example, the path OATH hashtag represents the word oath. This tree will help us quickly check if a sequence of letters on the board matches a word or its prefix. With the tree built, we start exploring the board using depth-first search, or DFS, from every cell. The goal is to find all valid words by following paths on the board that match prefixes in the tree. Starting at cell 0, 0, which contains the character O, we find it in the tree. From here, we explore its neighbors, moving to 0, 1 gives A, continuing to 0, 2 gives T, and finally reaching 0, 3 gives H, which completes the word oath. We add this to our result set. After backtracking, we explore other starting points, such as 1, 1, with the character E. Following similar steps, we find the word eat by traversing the path to 1, 2, and then 1, 3. Once all cells have been checked, the final result contains the words oath and eat. Now, let's consider a different example where no matches are found. The board is smaller, with the characters of B, C, and D, and the words list contains XYZ and ABCD. First, we build the tree for these words. The tree contains two branches, one for XYZ and another for ABCD. Next, we begin the DFS from each cell on the board. However, in this case, none of the paths on the board match XYZ, as none of its prefixes exist in the board. This means XYZ cannot be formed. The tree does contain the word ABCD, but as we'll see, the paths for it need to align with the board. Starting the DFS from 0, 0, the character A matches the beginning of ABCD in the tree. From here, moving to 0, 1 gives B, then to 1, 0 gives C, and finally to 1, 1 gives D, completing the word ABCD. This word is added to the result. Since XYZ cannot be formed and no other matches exist, the final result is just ABCD. Finally, consider the edge case where the words list is empty. In this case, the tree is empty, and there are no words to search for, so the DFS is skipped entirely. The output is simply an empty list. Here, we break down the time complexity of the solution into two main components, constructing the tree and performing the depth-first search, or DFS. First, let's analyze the tree construction. Each word in the given list is inserted into the tree, and for a word with an average length of L, this requires L operations. If there are K words in total, the time complexity of constructing the tree becomes O, K asterisk L. Next, we consider the DFS traversal. The search starts from each cell on the board, which has dimensions m by n. In the worst case, for each DFS call, we may explore all paths, and this exploration is limited to the maximum depth of the path, which is the length of the longest word, L. Since there are m*n starting cells, and each DFS call can branch in up to 4 directions, the total time complexity of the DFS traversal is O, m times n times 4 to the power of L, where 4 to the power of L accounts for exploring all possible paths of length L. Together, these two components define the overall time complexity of the solution. Now, combining the time complexities of tree construction and DFS traversal, the overall time complexity becomes O, K times L plus M times N times 4 to the power of L. For large L, the 4 to the power of L term dominates, making the DFS the most computationally expensive part of the algorithm. Moving on to space complexity, there are two key contributors, tree storage and the auxiliary space used during DFS. The tree stores all the words, and since each word contributes L nodes on average, storing K words requires O, K asterisk L, space. For the DFS, we use a visited set to track the cells currently in the DFS path. This set holds at most L cells, resulting in O, L, space. Additionally, the recursive call stack used during DFS has a maximum depth of L, contributing another O, L. Therefore, the total auxiliary space for the DFS is O, L. Combining these contributions, the space complexity is O, K asterisk L, for the tree and O, L, for the DFS auxiliary space. When we combine the space requirements of tree storage and DFS auxiliary space, the overall space complexity becomes O, K asterisk L plus L. However, since O, K asterisk L, dominates, the space complexity simplifies to O, K asterisk L. Comparing this tree-based approach to a brute force solution highlights its efficiency. A naive method would involve searching for each word in the list individually, performing a DFS for every word starting from every cell on the board. This approach has a time complexity of O, K times M times N times 4 to the power of L, which is significantly worse than the optimized solution. The tree-based approach reduces redundant computations during DFS by sharing traversal paths for words with common prefixes. This makes it much more efficient, especially when the word list is large and contains many overlapping prefixes. Finally, let's analyze the time complexity in different scenarios. In the best case, if none of the words in the list exist on the board, the DFS terminates early, and the time complexity is dominated by tree construction, which is O, K asterisk L. In the average case, practical constraints like visited cells and mismatched prefixes significantly reduce the number of valid DFS paths. This makes the time complexity closer to O, K asterisk L plus M asterisk N asterisk C, where C represents the average branching factor, which is typically much smaller than 4. In the worst case, however, all DFS paths are valid up to the length of the longest word, leading to the maximum time complexity of O, M times N times 4 to the power of L. Regardless of the case, the space complexity remains consistent at O, K asterisk L, as it depends only on the tree structure and the maximum DFS depth. In this section, we'll discuss some common mistakes that can arise when solving the word search 2 problem. First, a frequent issue is not handling edge cases. For example, if the board is empty, words are missing, or overlap occurs in unexpected ways, you may run into runtime errors or incorrect results. Testing edge cases, such as a single-cell board or duplicate words in the input list, is crucial to ensure your solution is robust. Another common pitfall is inefficient backtracking. If you don't prune unnecessary paths, the search space can grow exponentially. Revisiting previously visited cells or evaluating every combination without checks can make the algorithm unbearably slow. To avoid this, use a visited array or temporarily modify the board to keep track of visited cells. Next, ignoring word constraints can lead to wasted computation. If the problem specifies limits like word lengths or character distributions, pre-process the words, perhaps by sorting them by length or frequency, to reduce unnecessary work during the search. Lastly, once all words have been found, it's important to terminate the search early. Continuing to scan the board after meeting the goal wastes valuable computation time, so implement a mechanism to stop the search once the condition is satisfied. Now, let's delve into the importance of properly implementing a tree and key insights for interviews. When using a tree-based approach, common mistakes include not handling edge cases like words that share prefixes or failing to correctly mark the end of words. These errors can lead to incorrect results, so it's essential to test with datasets that include overlapping and prefix-heavy words. From an interview perspective, this problem is an excellent opportunity to showcase your ability to recognize patterns, specifically, how backtracking can be combined with advanced data structures like a tree to optimize brute force solutions. Interviewers also value systematic debugging, so be prepared to explain how you'd address issues such as infinite loops in backtracking or incorrect word matches. Furthermore, having an optimization mindset is key. For instance, a tree-based solution is highly efficient for searching but can consume significant memory. Being able to discuss these trade-offs demonstrates a deep understanding of the problem. Lastly, clear communication is essential. Be sure to articulate your thought process, especially how you handle edge cases and constraints, as this is often an area interviewers focus on. Next, let's consider related problems and alternative approaches that can help deepen your understanding of word search too. Some related problems include LeetCode 79, which is a simpler version of this problem where you only need to find one word on the board. Then there's LeetCode 208, which focuses on implementing a tree, a foundational skill for solving word search too. LeetCode 425, word squares, is another problem requiring the use of both tree and backtracking to efficiently solve. When it comes to alternative approaches, one powerful method is tree-based optimization. First, you construct a tree for all the words in the list. Then, as you traverse the board, you check prefixes in the tree to avoid redundant checks. This can significantly improve efficiency, though it comes with the trade-off of increased memory usage. Another approach is depth-first search, or DFS, with pruning. Using a visited array ensures that cells are not revisited during the same path, and pruning paths early if the prefix doesn't match any word in the list saves valuable computation time. This method is easier to implement than a tree-based solution but can struggle with performance on larger inputs. Finally, let's explore two additional techniques to optimize the search in word search too. First is pre-processing the words. By sorting the words by length or frequency, you can optimize the search order. For instance, shorter or more frequent words can terminate searches earlier, leading to faster runtime overall. However, this approach does require additional pre-processing time, so the trade-off is that you may spend more time upfront to save time during the search itself. Another advanced strategy is a hybrid approach that combines the strengths of tree and DFS. This method allows you to leverage the efficient search capabilities of a tree while using DFS to traverse the board. The hybrid approach can provide the best of both worlds, balancing search efficiency with reduced memory usage where possible. However, it is more complex to implement and debug, so it's important to carefully test your solution to ensure correctness. These techniques, while advanced, can provide significant performance improvements and demonstrate your ability to tackle challenging optimization problems effectively. Thank you for walking through this problem with me. Today, we covered how combining tries with backtracking can help solve word search too efficiently. Remember, mastering such techniques is crucial for acing interviews. Don't forget to like, subscribe, and share with your peers. Keep practicing and happy coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!